Welcome back. This is section 10.4 on the strengths of acids and bases. So acids and bases can be classified into broad categories as strong or weak. And this is all based on how well they transfer protons to water for the case of acids, or how well they accept protons in the case of bases. So in the strong category, a strong acid transfers 100% or nearly 100% of their acidic hydrogens to water when they're placed in aqueous solution. So every proton that can ionize off of a strong acid when it's placed in water will ionize off of it. A strong base, along the same lines, accepts nearly 100% of the acidic hydrogens that are donated in water solution. So strong acids and bases, I put them together in the strong category because they're both operating at like 100% efficiency. Acids are going to donate 100% of their protons or very close to 100%, and bases are going to accept 100% or very close to 100% of the protons they can accept. On the weak side of things, weak acids are only going to transfer a small percentage, usually less than 5%, of their acidic hydrogens to water. So if we think about the equilibrium reaction, these acid-base reactions are in equilibrium. With a weak acid, because they're only transferring a small percentage of their protons, that means the forward reaction isn't very favored. They're not making much ion. They're not ionizing very well. And so the reaction favors the reverse reaction because they're not producing much product, the product being the ion that they make. Weak bases, they only accept a small percentage of acidic hydrogens from water in aqueous solution. So again, I group these this way because I can remember the strong, because strong acids and strong bases, they're both do what they do as an acid or a base nearly 100%. So strong acids transfer about 100% of their hydrogens that are acidic, and bases accept nearly about 100% of the acidic hydrogens from water. And on the weak side, the acids and bases still, of course, act like an acid or a base, donating protons or accepting protons, but they don't do it as well. They don't accept very many protons if they're a base, and if they're an acid, they don't donate or transfer very many protons. So strong acids, they transfer nearly 100% of the protons, H+ ions, to water in aqueous solution. So for a strong acid, any old acid, HA, it's going to transfer nearly 100% of its proton, meaning that in aqueous solution, the acid is going to ionize 100%. It's going to turn completely into H+ plus A- when it's put into aqueous solution, and then this H+ can be transferred to water. So you make H3O+, and then you have A- left over. Because these reactions are nearly 100%, all of the proton that can ionize off of the acid is ionized. We give these a single-headed arrow to show that the formation of products is very, very strongly favored, that like all of the acid's going to ionize, and because all of the acid ionizes, you're going to make a lot of this hydronium ion product and a lot of this conjugate base product. So there's 7 strong acids to know. This is something that you might want to either memorize or put on flashcards or just like have them in your notes when you're taking quizzes and exams in this class. They're HCl, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, chloric acid, perchloric acid, and sulfuric acid. So I recommend getting to know the 7 strong acids, because anything that's not one of these 7 strong acids is going to be a weak acid. So if you can memorize these 7, then you'll always be able to differentiate a strong acid from a weak acid, because you just scan to see if if your acid is one of these 7. If it is, you can check off, okay, I'm working with a strong acid. And if it's anything other than one of these 7, it's going to be a weak acid. So that brings us to weak acids. They transfer only a small percentage, typically less than 5%, of their protons to water in aqueous solution. So most acids are weak acids. We only have 7 strong acids, and then every other acid out there, and there's tons of them, especially like in foods like malic acid and citric acid and acetic acid. They're all weak acids. So the general formula for a weak acid ionizing in water is the same as for a strong acid. The only difference is you have this double-headed arrow. So a weak acid, only a small percentage of the weak acid is going to ionize to make H plus A minus. Ionization is small. So because only a small amount of the weak acid is going to be generating these H plus ions, there's not going to be many H plus ions to react with H2O to make our products. So the reverse reaction is favored. The formation of reactants, or the reaction, is pushed to the left because most of the weak acid is just going to stay in its acid form as HA without ionizing, which means you're not going to make very much of the products. So a key thing to look for with weak acids is check for that double-headed arrow to show that it's an equilibrium reaction, that the reaction is going to be going in both directions. And for weak acids, the reactant side is favored. Because not very much of the acid is going to ionize, and we have to have the acid ionize in order to make our products. So if not much is ionizing in the first place, we're not going to get very much of these products produced. You should know the formula for acetic acid. It's the most common weak acid we're going to be talking about in this class. And I always point this one out because there's two common ways to write the formula for acetic acid. You can write it HC2H3O2. And I put the proton, the acidic proton, in red here. It's in the front on this method of writing the formula for acetic acid. It's also very common to write the formula for acetic acid CH3COOH. And in this case, the acidic proton is the one that's on the end. So when acetic acid donates its proton, which it doesn't too much because it's a weak acid, it favors the reverse reaction, so it favors staying as an acid. But when it does donate its proton to turn into ions, it turns into H plus C2H3O2 minus in this case. And in this case, with this way of writing the formula, it turned into H plus CH3COO minus. And they're the same thing. If you count up the carbons, the hydrogens, the oxygens, they're the same. They're just two different methods of writing the formula. This is how inorganic chemists tend to write it, and this is how organic chemists and biochemists tend to write it. Okay, so let's look at kind of comparing proton transfer in strong versus weak acids. So we have our general reaction for an acid in water. Any old acid in water is going to yield some amount of hydronium ion and some amount of conjugate base, depending on if this acid is a weak acid or a strong acid. So if our acid is strong, before proton transfer, we have 100% HA in solution. Right? There's been no ionization, so no protons been transferred to water to make our products. And then we put it in water, the reaction starts, the HA starts ionizing and donating a proton to water. And if HA is a strong acid, it's going to donate all of its proton to water. So after the reaction, we've generated all H3O plus and all A minus. We don't have any HA left because it's a strong acid. It donated 100% of its proton to water to make the two products. Each time HA donates its proton to water, it makes one A minus. And so at the end of the reaction, the concentration of H3O plus and the concentration of A minus is the same, because each time an H3O plus is made, an A minus is also made at the same time. If we look at a weak acid now, before proton transfer, before the reaction started, we have 100% of the weak acid in our reaction mixture, and then we add it with the water. And because the proton transfer is weak, the transfer of H plus is small. At equilibrium, when the reaction is stabilized, we still have a lot of HA left because not very much of it ionized to transfer a proton to water, which means that we have very low concentrations of both of our products. The concentration of both of the products is going to be equal because each time HA does transfer a proton, it's going to create one ion of A minus. So in these acid-base reactions, when HA does ionize, these two concentrations are equal because each time HA donates a proton to water, it's going to generate one A minus. And this will be important when we start talking about some of the math in these reactions and what are called acid and base ionization constants. Okay, so let's talk about strong and weak bases now. So strong bases accept nearly 100% of protons from water. The strong bases you should know for this class are the group 1A hydroxides. So metal ions from group 1A paired with hydroxides, they're going to accept nearly 100% of protons from water. What that means is that when you put one of these bases in water, let's take lithium hydroxide. It's going to turn into lithium plus OH minus because the base dissociates. And then because it's in water, the OH minus is going to take a proton from water. Water will act like a base and donate a proton to the OH minus. So it's this OH minus that's acting like the base and is accepting a proton from water. For weak bases only accept a small percentage of the protons from water. So a strong base, every OH that's generated from a strong base is going to be accepting a proton from water. That's what we mean by accepts 100% of protons. Weak bases are only going to accept a small number of protons from water. So the one weak base we want you to know in this class is ammonia, NH3, and this is its reaction in water. So NH3 has a lone pair of electrons. If you mix it with water, it's going to accept a proton from water. Ammonia is the base, it accepts a proton, water is the acid. But because it's a weak base, it's only going to accept a small amount of the protons from water. And so when we write the equilibrium, I kind of showed these arrows to show which way the reaction was favored. The reverse reaction is favored, meaning you're not going to produce very much ammonium and you're not going to produce very much hydroxide. Most of ammonia is going to stay as NH3 and not be accepting protons from water. And that's what makes it a weak base. So let's do a quick concept check. Which of the following equations would be a correct representation of a strong acid when placed in water? It looks like my arrows got off a little bit here with the formatting, but let's check these out. So we have HA plus H2O with equilibrium arrows showing an equal favoring of the forward and reverse reaction. We have HA, an acid placed in water, with an equilibrium arrow showing favoring the products and not favoring the reverse reaction. And then we have an acid placed in water with this arrow showing that the reverse reaction is favored and the forward reaction is not favored. So we want strong acid. When strong acids are placed in water, they completely ionize. And so when they completely ionize, all of the H plus generated by the acid is going to be transferred to water. And the transfer is going to be complete or close to complete. So because the transfer is complete or close to complete, the products are going to be highly favored. So we want the reaction that favors the product side. So that's going to be answer B, because it has this arrow favoring the product side. Okay, we're going to next talk about ionization constants for acids and bases. I'll see you then. Thanks for listening.